Good morning students, this is Junita Mukherjee from SS Public School. Today we are going to take the new part which I have told you that I will take the electric motor part today and electromagnetic induction. The next part of electromagnetic induction or maybe telling about the electromagnetic induction, how it is being followed. Electric motors in class 10th physics, magnetic effects of electric current. So let's start this particular topic, that is electric motors. Here we are taking two magnets N and S. There is a split ring we are taking, and this particular strip is there, that is ABCD. This is a kind of what you can say. It's a rectangular insulated copper wire which is taking in the form of ABCD. ABCD rectangular coil. ABCD is a rectangular coil which is insulated copper wire, and the coil is between the two poles AB and two poles of north and south. This is the split ring here, which is defined by P and Q, and brushes are X and Y, and it is connected with the battery and that of the key itself. When the key is on, it will, what happen to this particular thing is that it will move in the anti-clockwise direction, that is from here to here. It will move in the anti-clockwise direction. This particular B and C will come in this direction, and A and B will be coming in the top one direction, topmost direction, that is it is moving like this. Okay, if it is moves, what happens to this particular value is that there is a generation of the electricity in this particular motor, and the electric motor starts. How it is, let's see. An electric motor is a rotating device that converts the electrical energy into mechanical energy. The electric motor is used for the important components of electric fan, refrigerator, mixtures, washing machines and MP3 players, etc. An electric motor is shown in the figure A13.15, consisting of a rectangular coil ABCD of insulating copper wire. The copper is placed between the two poles of the magnetic field such that the arm AB and CD are perpendicular to the direction of the magnetic field itself. AB and CD should be perpendicular to the direction of the magnetic field itself. Okay, it should not be direct towards the direction of the magnetic field. It should be perpendicular, as you know that it's from the right hand rule itself. This not this rule, with the left hand rule. Sorry, with the right hand rule. This is the magnetic. This is the current, and this is the magnetic field. They are perpendicular to each other. So the ends of the coils are connected to that of the two halves P and Q of the split ring. The inner side of the halves are insulated and attached to the axle. The external conducting edge of P and Q touch two conducting stationary brushes X and Y respectively, as shown in the figure. Current in the coil ABCD enters from the source battery through conducting brushes X, follows by the battery. So from X the current is being entered, and from this it moves from this particular brush and then coming back to this Y position, and thus it is mechanically moving. This particular part is mechanically moved, and this helps in electric motors to generate, to move. Okay, so this is how the electricity is magnetic material is used to form the electric material, and thus the electric motors are moving, that is refrigerator, you can say electric fan, or mixtures and washing machines, computer, MP3 players, etc. So note the current in the arm AB of the coil from A to B in the arm CD to flow from CD, and that is the opposite direction of the current through AB. Now applying the Fleming's left hand rule for the direction of the current of carrying current, Fleming's left hand rule. So what is the Fleming's left hand rule? We have already been seen that this particular position of this position is the current, this is the field, this is the field itself, and this is the motion. So this is the motion, this is the field, and this is the current itself. This is current, field and motion. So from the Fleming's left hand rule we are able to find it out from this particular thing is which one is force, which one is field, and which one is current moving on. Okay, so we will be able to find it out. Then the conductor in the magnetic field, we find the force acting on the AB which pushes it downwards, while the force acting on the arm CD pushes it upward. So CD will be in the upward position and AB will be in the downward position. Okay, so AB will be downward position moving and the CD will be moving in the upward position. So this thing is moving downwards and this thing is moving in upward position. Okay, then what happens to this? That is in the anti-clockwise direction it is moving. Okay, not in the clockwise direction. So hence what happened? Thus the coil and the axle O moment mounted fleet to turn about the axis and rotate anti-clockwise. At the heart rotation, Q contacts with the brush X and P with the brush Y. Therefore, the current in the coil gets reversed and flow along the path DCBA. The current in the coil will be reversed. Current in the coil will be reversed DCBA. DCBA. Why? Because it is moving like this. Okay. DC is downward and AB is upward, is moving upward. So in this manner it is moving. So AB pushes it downward. AB is at the top and CD at the down. It is in the reverse direction. So thus what happens? The reversal of the current also reverses the direction of the force acting on the two arms AB and CD. Thus the arm of this AB of the coil that was early pushed down is now pushed up, and the arm CD previously pushes up is now pushes down. So CD will be pushing downward and AB will be moving. It is continuously moving. That's why. Okay, so what happened? Therefore, the coil and the axle turns half a turn more in the same direction. The reversing of the current is repeated at the half rotation, giving rise to a continuous rotation of the coil and to the axle. The commercial motors use are: first, an electromagnet is placed in a permanent magnet, place of permanent magnet, and large number of turns on the conducting wire in the current carrying coil and the soft iron core on which the coil is wound. The soft iron core on which the coil is wound plus the coil is called an armature. This enhances the power of the motor. So what we are using in the place of a permanent magnet, we are using an electromagnet in the place of permanent magnet. Large number of turns in the conducting wire we are using, so that we can be able to get the more and more kind of energy from it for moving. And soft iron core is used on which the coil is wound up, and thus the armature which is called the armature, and hence it's the power of the motor itself. So this is how the Fleming's right hand rule works. How does the Fleming's right hand rule works? I will tell you in the electromagnetic induction. As I told you in the electromagnetic, so this particular topic is being easily told, and I told you about how it is moving. Now this particular thing, that is electromagnetic induction. In electromagnetic induction, in induction, what happens? We are taking a coil. Okay, we take a coil. What we are taking? We are taking a coil. Here we are taking a coil of wire AB having a large number of turns. So A and B is the coil we are taking, and there are a large number of turns in it, and it is connected with that of the galvanometer. Okay, and what happens? There is a magnet here. So whenever the magnet is there, now the south pole will be there. Okay, so whenever we are moving this particular magnet towards this particular coil, what happens? Deflection is there in the galvanometer. Means that there is some kind of electricity generated in this particular coil when the magnet field is near this particular coil itself, which means that there is a current of establishment when the magnet is brought near this particular coil. This is what we call the electromagnetic induction. Now we have a theory behind it, is that we have this particular thumb rotating in this particular direction. So this is the motion, this is the field, and what is the induced current? This is the induced current. This is the induced current. This is the magnetic field, this is the motion, and this is the induced current position. This is the field, this is the field, this is the motion, and this is the induced current we are using. So which is very important is that you have to know what is electromagnetic induction, and you have to know what is the value of the motion and field and thus the induced current moving on the conductor. So movement of a conductor is defined by the motion, magnetic field is defined by magnetic field itself, and current induced in the conduction in the conductor is by the current itself, that is motion of a current itself. Motion of the current should be known where the field is and where the motion will be. So this particular thing is well over. Now some of the questions I need to discuss with you, which will be told in the next video. As time we have discussed here so many things. So electric generator we will discuss the next topic, and some of the questions we will discuss, and the geometrical electrical circuit is the last. So few topics are left. So learn well, and study hard for your final exams. Thank you, students.